Okay, I think we can start. We have more than 30 people already joining. So, good afternoon, everyone. And first of all, please, can you confirm if you can hear me well?
Yeah,
Yes, we can.
clear.
Yes, you could.
Oh, perfect. Um, I would like to welcome you to the 11th session of the Schlumberger SSA Reservoir Engineer Technical Sessions we have been delivering to you. The topic of today will be uncertainty and optimization workflows. And we will be focusing in detail on the sensitivities and uncertainties analysis. If you look into the meeting heading, there was also proxy modeling, but due to the time constraint, and we prefer to move the proxy to the next session. Although we will wanted to present to you certainty and optimization workflow. So I'll be handling this session together with Carlos Romano, which will present it to you, and I'll cover you the demo session moving forward. Please, if you have any question, just type into the chat window, and we will answer your questions accordingly. Or at the end, you can raise your hand and you can tell us which question you have or comment you may have within this session. So you are welcome, and through that, I will call Carlos, which will present to us this topic. Thank you.
Thank you, Henio. Hello, everyone. My name is Carlos Romano. I'm a reservoir engineer based in Rwanda. And Henio was just speaking. He's our technical consultant, our base here. Now let's go on. The agenda for today is going to be about sensitivity analysis and uncertainty analysis. This is a few topics that we'll be showing to you. The section today, as you see in the schedule, is UNO1. We still have UNO2. Proxy modeling was part of the section today, but because of time constraints, as Henio explained, we're going to move that to another section. And we're also going to cover assisted history matching for the next section and workflow creation. Now, let's start on the sensitivity analysis. Sensitivity is mainly used to gain insight into various issues and guide us decisions in which we understand the parameters that are worthwhile to investigation in detail. And with that, we reduce the parameters in order for our history matching to achieve higher productivity. Whereas uncertainty is used to study the impact of uncertain parameters in the model response. We are always used to run our simulations one by one. And with that workflow of uncertainty and sensitivity, we are able to use multiple realizations. If you're running just one scenario, single scenario, as you see in the image on the left side, we have a single scenario. The amount of tested that we can do in our model is still it's still vast. We can still do a lot of tests in that case. And sometimes when we're doing one by one, we're not actually covering all the space that we can in our simulation. If you look, for instance, here, you're just looking at the actual data is not yet completely covered, whereas our simulations is way above. Whereas if we use multiple realization, we will make sure we are testing many scenarios, and we are covering a wide range of cases, which go from high, mid, and low cases from our actual data. Saying that, now let's focus on sensitivity first, and then we go to uncertainty and in separate sections. In the sensitivity study, one might ask, what is the objective of the sensitivity study? The sensitivity study is used to gain insight of each parameter response in our model, in which we will rank the uncertain parameters in order of their significance, meaning that the parameters that impact the most is going to be on the top rank of our tornado plot, whereas the parameters that don't impact most on our model, we're going to be at the end. With that, we try to reduce the complexity of our problems, okay, which will help us in order to go forward with the model. Sensitivity studies are used many different ways if you're trying to calculate the cumulative oil production with to try to sensitize with the cumulative oil production with ejection rates. We try to get the best, the perfect, the impact of the water oil contacts, and also even if you're talking about the water breakthrough time to the fault sealing properties. And there is also a workflow that we try to follow when you're trying to do a sensitivity study. It starts with a response parameter definition, where we're trying to identify the key reservoir indicators of interest, the key parameters that impact our model. Then we move to parameterize the uncertainty, where we're going to define the ranges of that uncertainty parameters, the mean, the max, and the base value for that parameters. With that, we can run many different cases where we can use different techniques. Whereas we can use experimental design, we can use equal spacing, OVAT, meaning one variable at a time simulation runs to see the impact of each variable in our case. And we can also use Latin upper cube, where it's going to simulate using a wide ranges of random values. After all that simulation, we move to analysis, where we use tornado plots, tornado diagrams, or tornado plots to rank those parameters in order of their significance and impact on our model. At the end, we use distribution plots, where the plots that we are used to is our vector plots, where we can see the impact on our production rate or water production rates, you name it. And at the end, we revise the uncertainty matrix, where we're going to reduce the parameters and discard the ones that don't impact much on our model. Now let's go on step by step on what I just said on our workflow. Step one is to define the parameters, okay? We're going to the responses of the outputs of the simulators, okay, such as cumulative oil production and how that parameters are impacting the cumulative oil productions. Based on that, we're gonna define the response of interest, okay, meaning that we're gonna select which are KPOs in our model. Then we move to step two. In step two, we are defining the many attributes such as the range and the distribution that you want to use for our sensitivities. We want to make sure the parameters we are considering are in a continuous. If are continuous, we know which range they're gonna use. If they're discrete, we're gonna select the mean, the max, and the base value for that. Step three is to generate the case. We're gonna generate suitable simulation case, select the appropriate sampling technique. We can use equal spacing, we can use Monte Carlo, and the simplest type of sensitivity is the one variable at a time. The simulation is gonna run one variable at a time, and you'll be able to see how that is impacting, how each variable is impacting on our model. For example, if this is an example, if you have a set of uncertain parameters, you're gonna input that in the workflow for our reservoir, and then we're gonna investigate the influence of each input. On the right side, you see the tornado plot. You're gonna investigate the influence of each variable in our model. Step four is to analyze the result. As I was saying this in the previous slide, is the one variable at a time. Here we have a tornado plot. In this diagram, we have a range of variables. This is a range of parameters, and here we have the range of impact of the reservoir. The bar represents the impact of the reservoir. The longer the bar, the higher the impact, meaning that those parameters are here, those that are one at the very bottom are not impacting much on our reservoir. And also take in consideration that you need to pay attention on the time step that we are talking about. Because in different time steps, you might have a different, or the amount of impact in your model, it might be different. For that, we use cumulative tornado diagrams in which you're going to see the impact of all the parameters or selected parameters that you want to identify. Since you already identified the main parameters that impact most on your reservoir, then you can see how those parameters are impacting in all time steps in just one plot. Moving forward, we have also the distribution plots. Distribution plots, as I said, is the ones that we are most common with, is the cumulative oil production, is our vector plots, where we have oil production rates, water production rates, and so on, and displayed in with many lines representing many simulation cases that were run. After analyzing those results of the sensitivity study, what we want to do is revise the parameters definitions, remove all of the less important parameters, the ones that are not affecting most on our reservoir, and just stick with the ones that impact most on our reservoir. We can reduce the ranges to see how to reduce the amount of uncertainty on that parameters, and move forward to our uncertainty. Now let's go to uncertainty analysis. Uncertainty analysis is also uses the sensitivity results, which you see in the few slides. When you're talking about uncertainty, you're also talking about risk. Okay, risk, as the definition says, is the probability that an action will cause a loss or an unwanted outcome, whereas uncertainty is not something you are unsure of. And what you are trying to do here is reduce our uncertainty, because the risk is always there. We're not going to be able to get out of risk. So we're just trying to reduce the uncertainty in our model to make sure we are able to mitigate the risk and reduce the amount of risk we are exposed to when we are developing our field. In our model, uncertainties on any of the inputs to the reservoir are put it in our workflow, and then we investigate the distribution of the response to see and this investigation is going to rank our uncertainties in terms of cases, which would be our P10, P50, and P90. When you're talking about uncertainty, there are a few terminology that we're going to use a lot when you're talking about uncertainty. Those are the distribution, what type of distribution we have, normal, log normal, the measure of central tendency or variance, which takes in consideration our mean, our variance, and our standard deviation, our probability density function, which is a statistical function that shows all the possible values and likelihoods that a random value can take in a given range, our cumulative distribution function, which are on the right top are here, which at a given value x, it shows the probability that any sample from the given probability distribution has a value less than 1. And we have a complementary cumulative distribution function, which shows how often a random value picked variable is above a given value. For example, the x1 here on this low graph. Okay. Uncertainty distribution describe uncertainty values, and some of the terms that are placed here is the range, which we're gonna select our mean and our max value, the mean, which refers to the average of those values, and the standard deviation, which is a measure of how much sampled values differ on average from the mean value. Okay. For our uncertainty workflow, we also have a workflow that we use in Petrel. In that workflow, it starts with selecting our best case model, which uses most likely values of the input value or input data. Then we define the uncertainties. We're going to select the ranges, the mean, the max. We're going to select the type of distributions that we want. And after that, we perform the sensitivity analysis. The sensitivity analysis is just what I showed in the previous slides. We're going to find the most influential parameters, the ones that impact most in our model. Then we're going to perform Monte Carlo simulations to assess the ranges and distribution of the response from those parameters. We run many cases are simulated. We analyze those simulations using histograms. We analyze those simulations using the vector plots, using the PDF and CDF that I showed previous. And at the end, we select our representative models, which is our low, mid, and high cases. Now let's go one by one on those on the workflow. We start by selecting our best case model. Okay, we select a single deterministic model using the estimates that we are given from our GNG folks, and we use that model. Next step is to define the uncertainties, the ranges of uncertainties that we are selecting for each parameter. For each parameter, you're going to define the range of uncertainty that we want to use for that specific parameters, taking consideration that we are now focused on just the ones that impact the most. And after we define that, we can go to our sensitivity analysis. Here is an example of a tornado plot. And here we have defined many variables. Because now we're talking about uncertainty, we want to make sure we are covering all of the values that really impact our reservoir. We select all those values. This is our sensitivity analysis. We want to make sure which ones are impacting the reservoir. The ones that are less impacting our reservoir, you see the bar is sometimes just aligned, is not impacting much on our reservoir. We're going to cut off those values and just focus on those which really impact our reservoir. And taking those that really impact our reservoir, we perform Monte Carlo simulations, where the uncertainty is gonna combine all of the variables at the same time. Sensitivity uses one at a time. Uncertainty uses all of the variables at the same time, taking consideration the ranges that it was given to the simulation. From that, the many cases you run, the better it is, and we can select our P10, P50, P90, or low, mid, high, depending on where you are. And we are in a more comfortable shape to address decisions. For example, we are able to select the number of wells that we're going to use in our model, some of the well location, the injection rates, the operating pressures. And here we're giving an example of production optimization or field development decisions. We can also use uncertainty to run a history match, for example. Okay, there are many ways that we can use this tool to run to give response to the task that we are giving off. Now let's go to understanding quantify the impact of uncertainties. It's just uncertainties drive our decisions, and our decisions manage risk. And as I said, we want to minimize the impact of decisions you're not ready to make off. Okay, risk is always there. We want to reduce the risk. So we use those deterministic model that can mimic what really happens, and from that we can make better decisions. And using uncertainties, we are reducing the uncertainties that we have by just perforating there. With that, I think that's my slide. We make sure we reduce our presentation because we still have a demo to show today. Here is the calendar for the next sections. So far we are on the 11th section, UNO1, sensitivity and uncertainty. Our next section is going to be on the end of the month, on September 30. It's going to be about optimization, is our UNO2. And we're going to also try to squeeze in a proxy in the next section or a separate section for that. With that,
okay.
Go ahead.
Thank you very much, Carlos.
Thank
Thank
you.
you for this summary of the uncertainty. I will move on and start with the demo section. where we want to show you in a more practical hand how are we able to manage uncertainty and optimization in Petrel. The focus of today will be mainly the uncertainty workflow, as Carlo mentioned, on sensitivities and uncertainty. Please, can you confirm if you can see my screen?
Yes, Henio.
Okay, thank you very much. So we know that uncertainty and risks are always associated with the models. And this is a Petrel project. And here you have one model with the many wells. And we are displaying right now the porosity distribution. And we can see directly that the heterogeneity that the model presents and the modeling that leads into creation of this static model can lead also, for example, for static model uncertainty. Is my porosity distribution this one that we have here? For example, we can see other static property like permeability, and this is the permeability distribution for this model I have here. And we can see that is a heterogeneous reservoir with areas with high and low porosity and permeability distribution ranges. We know uncertainty is carrying throughout the full static model and dynamic model. And Petrel allows us to be able to assess and quantify these uncertainties using the workflows that Carlos has shown you. And what I want to show you is you have now a Petrel project with an Eclipse case. You can use Eclipse or Intercept. The workflow will be the same. And I want to show you the steps that you need to follow in Petrel to be able to run the uncertainty workflow. So as a start point, going into the simulation tab, you'll be able to find in the uncertainty and optimization process. If you click on it, you have this window where I will create a new process, and I'll call it here sensitivity. And through this process, what I need to do is to add my model, which could be an Eclipse case or an Intercept case, and add here into the case pane. So what will happen is that most of the workflows that we use to define this specific base case that we have here will be enumerated and aligned inside my uncertainty process. So here is where I have the freedom to apply any uncertainty related to the process that I have. For example, we have the petrophysical modeling. We know this is a workflow done by a geologist, for example. And here you can open this process in Petrel and define any parameter being uncertain. We know porosity and property distribution sometimes is very dependent on the seed number. So I can, for example, come here and select the seed has one uncertain parameter. So I put dollar, I can put seed, photo. Okay, so this is just one example of defining a parameter to be uncertain. Another example could be in terms of the minimum and maximum values of the porosity you have available. Please, could you mute your microphone? There is some background noise. Thank you. So if you have a minimum and maximum ranges of your porosity and this value is uncertain, you can, even inside your geological workflow, you can define this value as to be an uncertain value by adding the dollar sign which represent an uncertainty parameter within the Petrel workflow, and adding the parameter we are defining. This is maximal porosity, okay? And into this process, I click apply and okay. And what will happen is that within here, I have been defined two variables within my petrophysical modeling. The good thing and the value of doing uncertainty analysis in Petrel is that you are able to assess the uncertainties both in the building of the static models, which is what I just have done, putting variable into the static properties, and also into dynamic properties, such as your fluid model, your rock physics function, your aquifers, if you have aquifers available in your model, your strategy of developing. So all the processes that you have available in Petrel, you are able to define and apply an uncertainty parameter into them. For example, I'll come here to the aquifer. I will double click on this aquifer, which is on the south part of my model. The aquifer is here defined, and I can put a variable into my aquifer permeability. So I can put here dollar aquifer perm, okay? And this parameter will be defined as an uncertain parameter. Although we know that we have a lot of uncertainties in our relative permeability curves. And we know that the relative permeability curve are terms that they are dependent. If I change, for example, my minimal, my cornered water saturation, my critical water saturation, so those are parameters that need to be controlled because my critical water saturation can never be lower than my cornered or my initial water saturation. So I can define these properties, and if I define them, I can put dependencies into them in order to better characterize how these properties will be changing. So here I have minimum water saturation, and for example here, I can define in a variable for critical water saturation. Okay, so once you define it, it also will be characterized here as I showed you before. Let's say your production rates are uncertain and you want to put a variable into those. So here you have your developing strategy. If you're using intercept, you have your field management here as a workflow, and you can go to any of the parameters. I can go to the well pressure control, for example, and I can change in what is my bottom hole pressure for all the wells in the folder. PHP, apply, okay. So within this process, I'm able to define all the certain parameters I have related to the model I built. But could be a question you can make, which is, well, I think I need to customize this workflow. I need to add in some steps, or I need to add in some properties which are not defined here. So the uncertainty process allows you to edit. And once you edit this workflow, you are able to add, customize, adding loops, or create your own specific workflow that will characterize this model. For example, I can come here and go to select a specific workflow. For example, I can go to, let me just select completions operations, and I can say I want to create or add or change my completions. So I can add in the completions process inside the workflow tab, and then I can customize it by adding what will be the wells and what will be the completion log I will use here. So this workflow editor we have in Petrel allows us to characterize all the process available inside Petrel and be able to set a variable and uncertainty into them. I will come here and, for example, I will add another one just to show you as an example. So as I was mentioning, um, I can add various process into here in order to better define my uncertainty parameters. For example, I can add fault transmissibilities as an uncertain parameter. So I just want to define and find here my faults. And once I do it, I can add in to my workflow. And after that is done, I can define what will be the fault transmissibility parameter in this model. Okay, so within here, I can push in the workflow up and specify what will be my transmissibility. One very important thing is that once I have defined these uncertainty parameters, I can go to the variable tabs and will be within this variable tab that I'll be able to manage which one of these parameters behave. What will be the base value? What is the type of distribution better characterize these parameters? If it is a log normal, if it is a normal, for example. We are talking of porosity, but if I go to permeability, I can put the log normal, and I can define what will be the minimum value and the maximum value. I can put here, for example, I want my porosity to change between 10 and between 30. Now, for the purpose of time, we have an already built sensitivity case, which I will show you here. So for this one, what we have done, we have defined many uncertainty parameters, and those are in terms of my fault transmissibilities. Here are my faults defined, and I can specify what is my transmissibility, and I put the dollar value to represent each fault specifically. I can put one for all. I have added a calculator which I define my perm z to have a variable, which is my $kVkh. Also, in terms of the rock physics, we have put uncertainty parameters within the critical, the core water, the maximal mobility for the water. And I have defined as well grid property modifications where I'm changing the pore volume has a variable $sign. Okay, the same process I showed you before. You can build your own and characterize your own uncertainty. One very crucial thing is when we define the variables like we're doing here, we'll have the base values. The base values will be corresponded to those that I have in the base case, and I will set what will be the minimum and maximum, the ranges this value will change. And as I showed you before, I can characterize which distribution best characterize the property I am analyzing. One important thing relating to the relative permeabilities, I know they are dependent of the connect water saturation of the cores, so I can define functions. Through that, I come here to type, and I can select instead of uncertain, I can put in an expression, and I can type in any expression I want, which integrates different uncertain parameters we have in. So then Petrel will be able to have this uncertain parameter, which will be dependent of the variation of the gas chorus. Okay, and by doing this, I'm able to write full functions that will allow me to characterize the dependence I have in the relative permeability uncertainty. Okay, I also have added the pore volume as one of the uncertainties, and as shown you before, I can add uncertainties both to the static and dynamic process, and those I can put in as seed. So if I go to the main case here, editor, as I shown you before, and through that I can add in a process which is looking into the model creation on the property modeling, and on this process, let me just find it here. I will be able to add any geological workflow I want to include it, if not already present in my initial workflow. So let me just go to the process itself, find it to be able to add. Just bear with me 1 second. Okay, I can come here, add in the petrophysical modeling, and through here select anyone I need and put the variable as I shown you before. Okay, so this is how we define variables inside the UNO process in Petrel. So my variable is here, and once I come here to the variable, this one is a geological variable and is a seed. So I can put in the seed and tell you that I want to change how is the numerical distribution of this property will affect. Okay, so this is how we define. In the task, I'm doing sensitivity, so I have sensitivity by variable, and I will define which will be the number of samples I want to use. Since I'm doing a sensitivity, I'm selecting a minimum of 2 in order to assess what will be the minimum and the maximum. And I can use equal spacing sampling method, for example, or a Monte Carlo. Since we're doing sensitivity, an equal spacing could be most appropriate if I want to sample the minimum and the maximum value. If you click in the show sample values, I'll be able to see for all the uncertainty parameters I have defined, which values will be used. Okay, so once that is done, I click in test. Okay, I have a variable empty, sorry, it should be this one. And I will fix line 13, which is the base case, okay. I'll be doing the test and then I will run the simulation. Let me just make sure that my base case is aligned. Okay, I want to run this simulation using 2 processors. You can define how many processors you want to use. Wait command to finish if you want to run your simulation concurrently or not. Or if you want to use multiple realizations, you're able to select that within your defined simulation case. You can select as well if you want to run in your local machine or if you want to run in the cloud using Delphi. You're able to select this from here and any other specification linked to your simulation. Remember, this is the same way you do your case. You have your grid for the initial properties, your functions. We have to make sure that all the properties we selected, they are here. For example, the aquifer is here, the property modification is here, the fault transmissibility is here, which means the parameters that will be shared and changed through the uncertainty workflow, they'll be represented in your simulation. Through that, you apply, and then you are able to run the simulation. Now, for the purpose of time, I cannot run 34 cases right now. So I have already run this case, and I'll show you the result. So what I'll do, the cases I have run are here in my input case. I have done the sensitivity for all these variables I have defined, and they're here. And now I want to make a plot to see how are these parameters changing. So I'll select here the main folder and go. And there is a tornado plot, and I want to see the production plot for this tornado. So here I have the tornado plot, which show me which one of those variables I have defined before is impacting the oil production cumulative, which was the parameter I have selected here. And I can quickly assess and understand the ones that I should keep for uncertainty and the ones that probably will not have much impact in my uncertainty. Remember, as we go to the uncertainty, the less number of variables I have, the best control I have within the variation and impact of those in my final result. So the variables, there are certain variables that have lower impact into my oil production, I can remove, and those that are most impact, that have most impact, I can keep them. Now, this is the uncertainty, this is the sensitivity workflow. To do an uncertainty workflow is actually very, very straightforward. I can use exactly the same workflow I have created before, just create new, write a new name. I can put uncertainty 2, for example, okay? And very important here in the task, rather than sensitivity, I select as uncertainty, which means I want to vary all the variables together. I don't want to assess the impact of one. I want to see how all these variables impact. But remember, I have seen that some variables doesn't have much influence, and those that do not have much influence, I can quickly deactivate them in order to not be used for this specific study. So I can deactivate them, which means, sorry, this one should be, because this one, minimum port volume, has one of the biggest impact here, so I will keep it. But those that I have deactivated will not be used in the uncertainty workflow. Moving to the uncertainty tab here, here is where I want to select how many samples I want to have and which sampling method I want to use. The bigger the number of sampling you can do, the more smooth will be your distribution, the more smooth will be your CDF cumulative distribution function. We understand we may, in order to really fully assess those uncertainties, we could run more than 500 cases or 1,000 cases, which practically speaking may not be feasible. So we try to assess in terms of the hardware capacity we have, in terms of the simulation time it takes, how many uncertainty scenarios will be good enough to mainly characterize the spread of the uncertainty distribution. And you can select from different samples. Those are the samples methods we have available in Petrel. Monte Carlo, Beacon sampler, central composition sampler, CSV sampler. You can define in Excel a specific sampling method, equal spacing. For this case, I will use Monte Carlo, hyperbole, and I can select 50 cases. And through that, I will apply, test, and run this case as I have been defined. Let me see. I just have to define here on the simulation to make sure I have my cases aligned. Okay, apply. Okay, so once I run it, so 50 cases, so I have done already the simulation in order to save us time, and the results are here, and I have all the 50 scenarios I have run using uncertainty. How do I visualize it? So from the tornado plot in the sensitivity, I'm able to understand the ones that have most impact using tornado, and also using a cumulative view, which I'll be able to see through time which parameter constantly has more impact. But that is just seeing a specific behavior of one parameter. After running uncertainty, so I have here my cases. What I'll do, I will display it first. I will open a chart window. And in this chart window, I will want to display my base case field, and I'll put my oil production cumulative. And after that, I can select all the parameters I run as uncertainty and see just by that what is the spreading of the 50 cases scenarios I have run with those uncertainties we have selected to run. Okay? Through that, I can have a feeling how is the spreading in terms of cumulative production of those uncertain parameters in my ultimate recovery. Now, if I want to go in detail and understand how is the main distribution of these cases, I can open a histogram window, select all these cases I have run, and coming to the result charting, I'll be wanted to visualize the same oil production cumulative. And one thing very important that we need to do is to make sure that we convert into a collection. And here I have the distribution of my cumulative production. And I have here the P10, P50, P90 cumulative production from these 50 cases I have run. The more cases I run, as I said before, the more smoother will be this distribution curve available here. You can also display your cumulative distribution function and be able to see from the scenario you have how we will vary your cumulative distribution function and how is your P10, P50, P90. A question you can put to me is, well, very fine. Now you have run 50 cases, and these cases are out here. How do I know which case is the P50, for example? You can come to the spreadsheet, and here in the spreadsheet, you'll be able to see for each of the uncertain scenarios you have run, what is the value the simulator took as part of the Monte Carlo random distribution. For each one, what is the combination used? And you can see it. So this is my cumulative oil objective function here. And I can select what is my P50 case, which in this case is my case 81, which corresponds to the P50 cumulative production scenario. Okay, so I know that the simulation case 81 corresponds to the P50 scenario, which is one of the last cases we have here. Okay, so this is just a very summarized way to show you that Petrel allows you to be able to understand and quantify your uncertainty parameters by doing uncertainty inside Petrel, both static and dynamic, and be able to quantify the impact of how these uncertainties you have defined here and how much they will impact your cumulative production. And let's say that case 81, which is the one that corresponds to my P50, I want to replicate it and make this a model. So what I'll do is I'll click in case 81, right click, and I will create a workflow. So this will allow me to create a grid which has all the input parameters that we use through a Monte Carlo random simulation that will replicate case 81. And I can use this as my base case to any further simulation or optimization. So in the next session, we will be showing in more detail how do we use the uncertainty and optimization workflow to be able to do optimization, history match, assisted history match, and then proxy modeling, which is to define a function to better represent the dynamics of the reservoir and then reduce the simulation time. But for now, what I want you to actually retain is that inside the uncertainty and optimization process in Petrel, you are able to, number one, do sensitivity and uncertainty workflows. You are able to characterize your own reservoir, characterize its uncertainty depending on the behavior they have. And you have multiple algorithms which will allow you to better sample and better represent the variance of the samples that you have available. And you can easily assess and quantify, once you have run the simulation, the risk impact that these uncertain parameters will have in your model. So through that, I would like to finish this demo, and I would like to know if you have any questions. Thank you very much. I hope you can still hear me.
Yeah, thank you very much. Hello, Henio.
Hello, yes, I can hear you.
Yeah, thank you very much. We have a few questions in the chat window.
Okay.
So we can address those questions before other persons ask their questions, or while waiting for us to ask questions. So the first question from Raphael. So he's saying that he thinks it's very important that we explain the difference between uncertainty and the control parameter. So if you go to your dialog box, so we can explain what the difference is and where we need to use them.
Okay, perfect. So so in here, inside our uncertainty and optimization workflow, we have defined, as I showed you before, various uncertainties, which we think are parameters that we are certain in the value. Those could be any, from porosity, fault transmissibility, could be the distribution, the random distribution of a variable, such as a seed in your petrophysical modeling. So we need to make sure we define what type of uncertainty this is. So if we come here to the type, and here we have different controls, different uncertainty parameters. So uncertainty means that for the fault transmissibility one, I will have a minimum and a maximum, is a normal uncertainty definition, and I can choose what kind of distribution I have. So this is the normal uncertainty definition process. Now, if I have, for example, a petrophysical variable such as seed, seed is a numerical variable, is a random value. It does not make sense I put a minimum or a maximum value into the seed distribution because it's a random value and is not linear. In this case, I will choose the control mode seed by variable, which means he will handling this uncertainty in a different way compared with a certain parameter I have defined above in the fault transmissibility. If I have relative permeabilities and I'm changing, for example, Corey water or Corey oil, which has dependencies, so I need to define these dependencies. And in order to define these dependencies, it will allow me to set here an expression, and I can manually put which expression better define the dependence this variable has. So all of these parameters we have here will allow you to best characterize this specific uncertainty we have here in order to assess what will be each behavior and what will be each control mode. So those are the types of definition we have for the uncertainties parameters we have defined. Okay. I hope that answered the question.
Henio, let me just add to the explanation that you have provided on the uncertainty and the control.
Okay.
So when you talk about the uncertain parameters here, basically you are looking at those unknown parameters, those intrinsic properties of the reservoir that you don't know with certainty what the values will be. So that is why we call them uncertainty. But when you talk about the control parameters, then you are looking at those parameters that you can actually control from the user perspective or from the operational perspective. So let me give an instance. Maybe you want to do optimization, then you can decide the location of your well. You can decide the rate at which a well will produce. So all these are control parameters. Whereas the uncertain parameters are those ones that you don't have so much control except to take additional measurements to really reduce the uncertainties that are embedded in those parameters. So when it comes to the implementation of the workflow, what you do with your certain parameters is you use them in the uncertainty analysis or sensitivity analysis workflow that we've seen. Whereas the control parameters are used when you do optimization, because you don't change the uncertain parameters in the optimization workflow. There is no point. You can't be changing that. You don't have so much control on that. So you focus on, okay, I can change my rate and see which one will give me the optimum outcome. So this is another, in addition to what Henio already said, when you look at the difference between the uncertain and the control parameters.
Okay.
I hope that
great.
answers the question. Yeah.
Yeah, Raphael. So I hope that answers it because I think it's clear from what Sam and Henry have said. So I'll just chip in a bit before the next question. So we can address that in either history matching or forecasting approach, which Sam has explained and Henry have explained. So if you're doing history matching and you set it to control, what that means is specify. So Petrel would look for an optimum number to give you a good match. So you don't have control over the parameters. It gives you a good match based on what values that fits into your history match. So that is for history matching perspective. So for forecasting, you can also get like the best values to control your bottom fluid pressure or your rates and all of that. So it's just a value to for history matching, what should be the best value to give me a match? And for forecasting, what should be the best value to have the best recovery in terms of rate, bottom fluid pressures, drawdown, and all of that. So that's what the control parameters would help you do. So I just hope, Raphael, that answers. So the next question is from Revelation. The question is actually saying that in the variable section, there are formulas that we specified, same properties in the model star. So the question is, are they the same properties in the model star? And how does Petrel know what the mnemonics are in the equations? So remember when you specify the relationships using equations and expressions in your uncertainty dialog box. The question is it the same thing as what we have as calculators in the properties tab? And how does Petrel know these mnemonics?
Okay. In terms of the expression, Petrel understands the normal calculation and functions, mnemonics, the same that used to do any calculator, addition, multiplication, so on and so forth. So logarithm, all of those Petrel is able to understand and calculate. But the difference here is these expressions will have a variable. For example, if you look to this expression here for the KRWM 0.4, it is a function which is dependent on the variation of the gas core, and this is a variable. And I have defined this variable here. So I have the dollar and G. I know is 2.5 and can vary between 1.5 and 3. So that means once the NG varies, the value that will be given to the KRWM will be a function of the new value that is chosen for the NG. And through that, Petrel will answer and calculate this formula and find what will be the correspondent value of the KRW. So that means all these functions here, they are dependent on the variation of the gas core. And this is how the expression will work within the uncertainty workflow. I hope
okay,
that
thank you very
answered
much, Henio. I think, yeah, I think so too. I think there's a comment. I think that should answer the question. So maybe you can have questions from other participants here.
Okay. Do we have any question in the line? If you have a question, please just raise your hand, and we'll be happy to answer. So I see Oyeyemi. Please go ahead.
Oh, thank you very much for that wonderful presentation. I believe that a proper understanding of how to quantify uncertainty is very important, be it structural and contact uncertainty of fluid and rock uncertainty. My question is, I would like to know if Schlumberger has a reference document that can guide user on how to define the ranges and the applicable distribution for us to handle the uncertainty very well before we proceed with for us to define the uncertainty very well before we proceed with the sensitivity analysis. That's my question, sir.
Okay, thank you very much. So actually, this is a very good question. Honestly speaking, there is bibliographies, and you can find in a lot of papers ranges of distribution of some specific parameters. We know permeability could have a logarithmic behavior. Porosity could be normal. So it will depend on each uncertain parameter you have and on the knowledge that you have within your field or analogs. What will be the ranges of these uncertainties? If you don't have, then we need to use that common sense, which is probably what you're asking. If we have a database which shows the type of distribution of each of the parameters. So for the basic, when I mean basic is if we look into porosity, permeability in a sandstone, in a carbonate. So there is many papers which have been compiled, which will show you in terms of analogies from different locations. What was the distribution used? So you can use that as an input if you don't have much knowledge on it. But it will all depend on how much study you have from your field, how much understanding you have from your specific reservoir. That will actually be what will characterize the ranges of these uncertain parameters that you have and the expected distribution it will have.
Hello?
Hello, Sam. Yes?
Yeah. So just to, Mr. Yemi, just to add to what Annie already said, the main thing in the uncertainty propagation exercise is to spend quality time to frame the problem very well among the people in the asset team. So framing actually takes the bulk of the work. And the outcome of the framing will be that input parameter metrics that will show all the uncertain parameters that have been identified by the entire team members who maybe were involved in the actual study. Then on that basis, you define all the inputs, all the parameters. You start with the, for instance, you can say you have structural uncertainty. But how do you parameterize this? You have to find a parameter in the module that can translate to that will help you to mimic that. So this will be defined. Then you move on to defining what is the range and so on and so forth before you move on to a realistic distribution selection exercise. So it's a whole lot of, and this is where people spend time. When it comes to the implementation, it's very easy in the tool. But before you get there, you have to spend quality time to frame the problem. Now, coming to the question on, like Henio said, there are a lot of concepts out there. Maybe porosity is normal and permeability is normal. But sometimes most of these, they also vary in your data. From your input data, you can infer a lot of these. From the Schlumberger end, from the experience, we've done quite a lot of uncertainty studies for clients. We have some collections, but I guess it will vary again from field to field.
Okay, yeah, I hope that answered your question.
Yes. Thank you very much. Yeah.
There is, I saw at the Google, you had a question?
Yes. Thank you for the presentation. The question I want to ask is with regards to the gas condenser reservoir. So what I want to find out for Schlumberger, if you want to characterize the trap gas, the gas condenser reservoir, and condensate banking, how will we do that in terms of defining it, and also, just defining it first before we put in the ranges.
Mm-hmm. Okay, thank you. So basically, that will depend on how we set up the model. Okay. So, and also, what are your main uncertainties? Because the process we're doing here is to uncertainty and optimization. But let me give you an example. Let's say that you have uncertainty in your PVT. And because you have uncertainty in your PVT, in your equation of states, that may impact the rate that you may have condensate banking, for example. Yes. So if that is your uncertain variable, you are able to come here and define different fluid models which will be able to characterize your level of uncertainty in your fluid composition, which ultimately will impact how your model will run and how your trap gas, or heterogrades will be formed as the pressure changes across the simulation time. So if you do that, then using different fluid models, different equation of states, you can see which one, what would be the highest, the low, and the impact in the cumulative production. This could be one of the ways to be able to assess this. Although that will also depend on what is uncertain in your specific case. Because could be just a matter of pressure maintenance. And if it is a matter of pressure maintenance, you can come to the defined simulation case, for example, and change different strategy where you vary the rates and the bottom hole pressure. So that could be also another way that you can manage this kind of reservoir and see the impact or what kind of operating conditions you can have in order in order to reduce those. Could be also a matter of well location. So how many wells you have and how much you will produce. Then you can add in another workflow where you can add in and take wells and see what kind of optimal number of wells you need. So it will depend on your developing strategy, on the uncertainties you have in your reservoir. That could be the fluids, the petrophysical también, that also impact. And then you characterize those. And the ultimate assess point will be those that you have asked. So there are different ways to characterize it. And I think those will be aligned with the ones that you are most uncertain with. And you can characterize that here within the UNO workflow.
Okay, maybe I can add to what you said. Thank you, Henio. So Jaja, for example, if you have different fluid models based on what Henio has talked about, you can create the fluid models. So those are going to be like objects. So if you look at what we've defined here today, we define variables as numbers. You have objects, for example, you have a property that is different, like a different property model completely. You're not multiplying, you're not subtracting, but a completely different model. You can use the reference project list to drop that as an object. So if you have like 5 or 6 or 4 fluid models, you can drop them as different objects. So they can be used as part of the facilities to run your case for you. Yeah. So if you remember what Samuel talked about, so whatever you're defining here is based on what you think is applicable to your field. So for example, if you are relating to condensate or trap gas saturation, so what we use sometimes is what we call the Lance correlation, where you have the Lance coefficient, which you can specify as variable. With that variable, it will give you different calculations of the trap gas saturation or residual oil saturation. So if you define your Lance coefficient as the variable in here, it's going to give you different recoveries and different trap gas behind your gas as you produce your reservoir. So once you do this, so I'm sure you can replicate whatever scenarios that you want to do. So what you have in here, it's very robust, allows you to do whatever you want to do, as long as you know what you want to do. So I hope that answers the question.
Yeah, Limi, thanks.
So yeah, you're welcome.
Thank you.
You're welcome, yeah.
Hi, Henio.
Hello, hi.
This is Anwar.
Hi, Anwar.
My quick question is regarding the water breakthrough. Normally, you change, you do a variation on the saturation, right? The visible water saturation. So my point is, in order to match, right, in order to get it as close as possible. My point is, when you have the influence of injection later on in the field, how do you actually try to compensate it? This is my question.
Okay. So I think the next session on that we'll have on on assisted history match and optimization will show you a little bit more detail on the workflow we have to help inside the uncertainty and optimization process to optimize. And that annual could be in terms of the injection rates, the critical water endpoints, and also the permeability you have in a specific formation, which will impact also the mobility of the water and how fast you will produce. Now, within the UNO workflow here, we can characterize all of these uncertain parameters we have. We can characterize the injection uncertainty. We can characterize your miscibility curve, your endpoints, and you can characterize your permeability and how it varies. So all of these you can define. But once you go to the optimization, which could be through uncertainty, then is where you, through uncertainty runs, which is a combination of all of those, see the impact it will have together. So that will be covered in the next session, which is the optimization process, which will be follow up in the next session. So it's this one here. First of all, what you have to do is characterize those uncertain parameters, like I showed you today, and then see how is the combination of them impacting. For example, let's say I have run 50 uncertainty cases like here. You are able to display and see, for example, what is the water production for each one of those, and quickly filter out which model, which combination is give you the one that match your model. This is a way to use the uncertainty results to quickly filter which one match your historical data. And that will definitely calibrate the injection production that you know, align with your irreducible, your critical water saturation, and your mobility in the reservoir. We should show you what is the, well, we should try to match the actual field behavior. So it is a combination of steps, and I think optimization will be the best way that you can use to help you match your history using uncertainty workflows. That will be covered in the next session in more detail. Now we just covered the uncertainty workflow. But yes, you can do that, and you have seen it partly today, which is just the definition of the uncertainty. And next week, you see how to handle and how to optimize and fine tune each one of these parameters in order to match your historical data.
All right, thank you.
Okay, do we have any more questions in the line? Okay, so if we do not have any more questions, I would like to thank you all for attending this presentation today. And I will one more time reinforce that the next session will be optimization on assisted history match. So that will actually, it is a continuation of this session we had today, and we'll address in more detail in terms of the workflow some of the questions you have put, which is how we can use uncertainty to optimize our models to match our history. But I would like to reinforce that if you have Petrel, you have this process available, please use it. If you need any support to the uncertainty definition and sensitivity, please let us know. And we count on you on the next session so that we can cover this other part of the uncertainty process. Thank you very much to all. And of course, stay safe.